The history of the Institute of Physics of Materials dates back to 1955, when it became a part of the newly established Czechoslovak Academy of Sciences. The mission of the Institute is to elucidate the relationship between the behavior and properties of a broad class of materials. This insight opens the pathway for the optimization of microstructure, properties, and to design novel materials that are more efficient and durable. Speed, efficiency and reliability are today's trends in the mobility of people and goods. Our research focuses on the new metallic and non-metallic materials that can cope with these challenges. The most obvious examples are the aircraft engines and the axles of wheeled vehicles. In our laboratories, we carry out fatigue measurements on samples exposed to the environments that mimic real operational conditions. Among the standard measurements are the estimates of the susceptibility of the material to fatigue and the velocity of fatigue crack growth. The fatigue characteristics of new materials for the aircraft engine blades are being tested up to the temperature of 900 centigrades. By putting together the individual pieces of puzzle collected from experimental measurements, simulations and structure analysis, scientists obtain a complete picture of the fatigue behavior of the given material. This systematic analysis plays a central role in certifications, recommendations for the material selection, and improvements in manufacturing of individual structural components. Another type of cyclic loading is the thermomechanical fatigue that is common during the operation of gas turbines and turbo compressors in modern combustion engines. At the heart of the laboratory is the electro-hydraulic pulsator that is capable of simultaneous cyclic mechanical loading and temperature control. An important property of the materials exerted to mechanical loads at high temperatures is their susceptibility to creep. Creep is a limiting state of the material that determines the efficiency of aircraft and other types of combustion engines. We carry out these creep tests up to the temperature of 1400 centigrades, which is a factor of 2 higher than the temperature of creep failure of standard structural components. The creep tests take usually a very long time, and thus a large number of creep testing machines available at our institute is a necessity. The most important result of the long-term creep testing is the dependence of the deformation on time. The laboratory of brittle fracture determines the fundamental mechanical properties of materials under the conditions leading to their sudden failure for static and dynamic loading. The impact bending test determines the fracture toughness and other characteristics of materials under dynamical loading. Detailed evolution of the microstructure in materials subjected to impact loading can be analyzed by a high-speed camera that captures the images with the frequency of 150,000 frames per second. The outcome of testing is a sample broken into 2 pieces that contain fracture surfaces. These are analyzed carefully by fractographic methods that use electron microscopes. The Institute of Physics of Materials does not focus only on mechanical properties, but also on the electrical and magnetic properties of materials. As one of the partners in the Central European Institute of Technology, CETEC, we utilize a wide range of the state-of-the-art equipment that is central to deep understanding of the links between chemistry, structure and physical properties of materials and their modifications due to different synthesis and previous thermal and mechanical treatments. Studies of the microstructure of materials require large magnifications. This scanning electron microscope can image details that are approximately 10,000 times smaller than the thickness of a human hair. Besides magnifying the surfaces of microscopic objects, this equipment is also indispensable for chemical analyses, studies of grain orientations in polycrystals, and for the milling of the material by focused ion beam. Here we see a typical manifestation of the fatigue damage, the so-called persistent slip band. By analysing its shape and amplitude profiles, we can estimate how quickly the crack will grow, and thus to predict the remaining lifetime of the structural component exposed to the given loading. This information plays a crucial role in the design of new, more durable materials. The transmission electron microscope is used to analyse the structure of thin foils with thicknesses up to a few hundreds of nanometers. The resolution is so high that one can image individual atoms. This microscope is an indispensable tool in the analyses of the structures of extended defects, crystallographic analyses, and for the estimates of local chemical content. It is most frequently used to study advanced steels and superalloys. A completely different view of the behavior of materials is offered by computer simulations. At the fundamental level, they provide estimates of the theoretical strengths of materials. In order to understand the interplay between the microstructure and mechanical properties, we develop a hierarchy of theoretical models that describe the behavior of the crystals of metals, semiconductors and isolators in a wide range of temperatures, loading conditions, and the rate of external fields. Our numerical models have proven efficient to identify weak parts of structural components that are prone to failure. These may lead to materials damage or even its fracture under real operating conditions. Our research efforts employ a full spectrum of both modern experimental methods and state-of-the-art computer simulation models. These are utilized by a coordinated team of renowned scientists, assisted by a number of PhD students, postdocs, and young researchers. These people are the true value behind the success of the Institute of Physics of Materials.